exam is tell and you're going to have to tell what type of model would best go with that. Is looking at the points to see, do they look kind of linear? Because these are going to be more real world, usually real world type of problems, so your data is not going to be in a perfect straight line. But if it's fairly in a straight line, you're probably going to go with linear. So linear looks something like this. This is an example. If you're given a table, you can look at the first difference. If the first difference is relatively close to the same thing, it's probably going to be linear. Quadratic, they make kind of a U shape. If you look at a table, you're looking at the second difference. The second difference is relatively the same-ish, close. And then, or exponential, kind of looks like half of a quadratic almost. You're looking at the y values kind of multiply by the same thing. They're close. Like this one times 2, 1 times 2 is 2. 1.9 is pretty close. Okay, times 2, you're getting pretty close. So it's relatively close. So let's look at some data points and graph them to see what type of model that. So we have 0, 11, and that only goes up to 10, so it's about up there. Oh, 8.2. 4, 6, 8. What do you think those points will look about like? Do they look more like a straight, like they would form a straight line? They look pretty linear to me. Those look like they form a straight line. If we look at the first difference, so if I do 11, I can see this is negative 2.8. 5 minus 8.2 is negative 3.2. Negative 2.7. Negative 3.3. Be the same, but they're relatively close to 3, negative 3. Okay, so it looks linear. It's never going to be perfect. Sometimes you might think one looks a very perfect set here. If we look at number 2, oh, we need to put on here linear. Number 2. Now, one thing that if you're going to increase by the same thing every time, for you to just be able to compare it like that. If perfectly spaced, I'll show you what we do instead. For 10, 3, 5, 2.4, 7, 3, and 9.7. What would you classify that one as? I would say exponential. Yep. And if you look, 2, it's pretty close. It's linear. Number 3, we've got negative 1, 2, 1.5, 2. What do you think on this one? Yeah, this one would be quadratic. If your y values, if they like increase and then decrease again, or decrease and increase, if they change, like they get bigger than smaller or vice versa, it's probably going to be quadratic. That's the only one that does that of the 3. Okay. And then number 4, got negative 2, 2, 1, 3. This one's kind of harder to tell. I would probably, just by looking at this, I would probably say exponential. You could, but if I look, let's see, this is, so if I look at what's being added, if I want to check my first and second differences first, this would be 1, 1.5, 2.25, 3.5, this is 0.5, 0.75, 1.25. So, I mean, in the grand scheme of things, 0.5 is pretty close to 0.75. But if I look at multiplying, 3 divided by 2, 4.5 divided by 3, 6.75 divided by 4.5 is 10.25 divided by 6.7. That's way closer to exponential. So they're way closer to multiplying by the same thing than they are to having the same second difference. So I would go exponential. Now, there is another way to check to see if a model is appropriate or not. And what I mean by that is if I give you this data and I say use your calculator to come up with an equation. You're going to go to L1, L2, but you have to pick. Am I doing the exponential regression? Am I choosing that option? Am I choosing the quadratic, or am I choosing the linear? Do I write which equation? Now, we know by looking at this, pick the quadratic one. But using the residuals, that's a way that we can tell if you picked the right one. And sometimes it's not a perfect pick. Sometimes Maybe 2 of them might get close to the data that you have. But we look at the residuals. And you've seen this word before a little bit. So a residual is, well, we'll get there in a minute. When we create a model, so when you go to your calculator and you create the equation, you do the linear regression or the quadratic regression, that model just predicts. It predicts values. It's like based on what's happened in the past, based on all of these data points. Again, they're not perfect. Real world data is not perfect. We can say, okay, going forward, I can predict what it will be. Is that prediction always going to be perfect? No. If you look, companies predict what their sales might be 10 years from now. There's lots of things that can change. They're not going to get it down to the cent, but they might get close. The residual is the difference between the actual value and the predicted. So it's basically how far off was it in real life. Remember, we did the starburst activity. So we could predict how many starbursts. And Mr. Adams walked in, he did it, and we looked at our prediction, and it was pretty close. But it's not perfect. There will always be a little bit of variance. Ideally, there would be none. Ideally, it would be perfect, but it's not. So a residual is A minus P. It's actual first minus the predicted. If the residual is positive, the prediction is an underestimate. If the residual is negative, the prediction is an overestimate. When we first did this at like the end of the last unit, we didn't even test on it. We drew out a residual plot. You won't have to draw those on the AP exam. Like, that's a for sure thing. You will only have to look at them and do like one little type of question with them. It's not going to be a huge part, and we'll talk about that in just a minute. So here we are. The weight of newborn babies can be modeled by a linear function for the first 4 months after birth. I feel like this is the same one that we already did. It's fine. Selected values for the weight in kilograms of a particular newborn baby are given in the table below, where T represents the number of months since birth. So this is one specific baby. And they weighed the baby at each month. This is just one baby. Is every single baby going to grow at the exact same rate? Nope. Are there factors that can cause a baby to grow faster in certain times and maybe lose weight or not grow as fast? Yeah. A baby is not going to grow at a perfect rate every time, but it's close. So use your regression capabilities on your calculator to find a linear model of the form y equals a plus bx of the weight, da 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 da. So, calculator. How do I get to my lists? Stat. Edit. If you want to clear out your list in one motion, highlight L1, hit clear, enter. Highlight L2, clear, enter. Get your data. And then how do I actually get to the equation? Stat. Go to Calc. And this specific, it told me in the question, it's linear. I could have looked, it's close to about adding 1 every time-ish. Okay, so it's linear. I would have picked a linear model for this one anyway, but it told us. There's actually 2 options for linear. I think number 8 is the one that's most commonly used. L1, L2. We want to go down to the store. We want to put that in Y1 because we're probably going to have to do some more with that equation. That way we don't have to type it in again. You may remember how to do that? Alpha trace. Good. Calculate. So it's y equals 3.34 plus 0.8x. That is the best, that's what they would call the line of best fit that you did in Algebra 1. So use the model found to predict the weight at 2.5 months. So you have 2 options. You can just plug a 2.5 in for x, which is really what we're doing. Or, remember, you can go get your y1, and then in parentheses right beside of that, type in a 2.5. And it will plug in 2.5 to whatever you've got in y1. And as long as you stored that in the last step, it's there. So 5.34 kilograms. Now, that's what was predicted. That's what our model, like based on our other data, we think it would be 5.34. But it's not likely going to be perfect. The actual weight of this baby was 5.5 kilograms. We want to know what's the residual, and was that an over, or was our model, was our prediction an overestimate or an underestimate? Well, I can see it's less than, so I know it's an underestimate. But so if we do our residual, A minus P, actual minus predicted. So 5.5 minus 5.34 is 0.16. And so it's a positive number. Underestimate. We want that as close to 0 as possible. The closer to 0 it is, the better our data was. Here's the type of question that you will see on the AP exam. This is an easy question to get. Is the model appropriate? So, you could put this in, and I could count off. One of you could do linear, one of you could do quadratic, and it would give you an equation. It would give you a quadratic equation. You could do exponential, and it would give you an exponential equation. But only one of those is the best choice, or the most appropriate choice. We know it's linear because you can just look at the numbers and tell they're about going up by the same thing. So it's supposed to be linear. But the way that you tell is you look at the residual plot. You would be given a picture of a residual plot, like one of these. If you're looking at the plot, if you do notice a pattern, some kind of pattern, the model is not appropriate. You've got to know that. If you see a pattern and it's like a quick glance, like don't study. If you sit there and try to study it and find a pattern, yeah, you might find one. But if you just look at it and say, yeah, I don't see a pattern, then that's what you want. You want no pattern. No pattern is appropriate. You kind of just want them, you're going to have a darker line in the middle. You just kind of want them like jumbled up around that line. So the same data set was used to create a linear, quadratic, and exponential model. So We had data set. I said, okay, this row, use your calculator, come up with linear, quadratic, exponential. And you all got your own equation, and you did all of the residuals. You did all the a minus p, a minus p, a minus p, and you all plotted. And this is what you would get. These are the three things. Which one of those do you think has the least pattern? Linear, quadratic, or exponential? Exponential. The linear, I mean, it follows a curve like that pretty well. Quadratic follows that curve. These are just kind of like zigzaggy. That's what we want. We want it to look like the exponential. We don't want a nice straight line. We don't want a nice curve. Okay, so the one that's the most sporadic. So whatever data set we had, the exponential was the best. If we were going to look at the actual graph, we would see it would follow an exponential pattern. Now, if you have examples involving area, this is just kind of a quick, like, if it's area, if it says anything about area, it's going to be quadratic. Like that's, because area, your units are squared. So quadratic is squared. Okay. So determine if the following residual plots show an appropriate model or not. We're just going to put yes or no. Appropriate or not appropriate. Number 8. What was your first instinct? No. That's a pretty, like, it follows that right there. What about number 9? I would say yes. They're pretty like spacey. I mean, like I said, if you study it, you could be like, well, it's like a, okay, it's kind of like that, but no, I would not put that as a pattern. What about number 10? Yeah. I would say put yes, that's appropriate. No pattern, it's appropriate. 11? I would say no. 12? I would say no. 13? I put yes on that one. So some questions. So you'll see multiple choice questions. And like let's and like your answer choices, you will have, like, it's not going to be either appropriate or not appropriate. It's going to be appropriate, no pattern, and appropriate because there's a pattern. And it's going to be not appropriate, no pattern, not appropriate, pattern. So first of all, you should look at that and be like, well, that's definitely appropriate. Like, it's pretty, like, just jumbled. They're just jumbled. But then you got to look, you got to remember, okay, appropriate means no pattern. Okay. Appropriate and pattern don't ever go together. Cross those out. Not appropriate and no pattern never go together. Cross that one off. Like, these come up. Like, if you see anything with residuals, and I think you will see that on the AP exam, like, that's a just remember no pattern. No pattern is appropriate. And no calculations would be required on this. Like, this is a get this question right type of deal. Okay. So, one other thing. If you have a table, and your X values don't go up by the same thing. your x values. You can't just be like, okay, well that's 1, 1, 1, 1. That doesn't work because these are not equal length input values, I think is the phrase. Your x values don't go up by the same thing. So you really, if this is the case, if you want to find the first difference, if for some reason that's what you need to do, you really have to do like the full slope. You have to do like 6 minus 5 over 2 minus 1. Six minus 5 is not 4. What am I doing? 1 over 1. 1 over... I have no idea what I just did. And then you would do 7 minus 6 over 5 minus 2. So 1/3. And you would go down. And we did that early on in the year, but it's been a long time since we did that. So this one, if I kept going, I'd probably be like, yeah, that's not linear. Even though these went up by 1 every time, you can't compare that because the x values were not spaced out evenly. So you have to watch that.